Today we're going to carry out the AC analysis of the common collector configuration. The first step is to draw the R sub E model for the common collector. Hindi na tayo mahihirapan for the R sub E model ng common collector. It's because ang R sub E model ng common collector is the same with the R sub E model of the common emitter. So let's recap the R sub E model of the common emitter, which again we will use for the common collector configuration. For the input side, we have the base terminal and the emitter terminal. So ang nasa pagitan nila is yung resistance na beta RE, which we have derived in our previous video lecture. Sa ating output, we have a dependent current source, which is equal to beta I sub B, which is also equal to I sub C. These are all AC parameters, and ang ginamit ko dito is yung NPN na BJT. That's why ganito ang direction ng ating dependent current source. Although, you can also use a PNP BJT, but you will have the opposite direction. Alright? This is our example from the previous lecture. We have derived the DC I sub E for this one. So kinakailangan natin yung DC I sub E is because it will dictate the level or the value of the R sub E or the AC emitter resistance. Diba we have the formula na dinerive natin. R sub E is equal to 26 millivolts divided by I sub E. Kapag nakuha na natin yan, pwede na nating i-substitute dito sa ating R sub E model. Alright? So let's calculate first R sub E. So this is equal to 26 millivolts divided by 2.06 milliamperes. We have an R sub E of 12.62 ohms. So we can write down the value for beta RE dito sa ating R sub E model. We can just replace the value of beta by 100 kasi yun naman yung given. And then this is 12.62. Therefore, beta RE, so let's write it down here. Beta RE is equal to 100 times 12.62 ohms equals 1,262 ohms or 1.26 kilo ohms. So that is the value for beta RE. After getting beta RE, we can write down the value here sa ating R sub E model. The next step is to zero out all DC power supplies. In this case, ang supply natin is 12 volts na VCC, which is a voltage source. We can zero that out para makuha nating AC equivalent circuit niya. To zero that out, i-draw natin itong VCC sa kanyang standard schematic symbol. So this is also the same with the symbol ng kanina. We have 12 volts na VCC. Next is we're going to short out the terminals of VCC para ma-zero out ang ating DC source. You do not do this in real life, You do not short out the terminals of a power supply in real life. This is just done for computational purposes. Since the voltage source is already zeroed out, ibig sabihin, yung collector natin ngayon ay nakakonekta na sa ground. Therefore, we can remove this one. Magiging wire na lang siya papunta directly sa ground. Right? The next step is to zero out, or rather to short out yung mga coupling capacitors natin, because under AC, coupling capacitors are considered to be shorted based on the formula for the capacitive reactance, which is equal to 1 over 2 pi FC. Kapag mataas yung frequency natin, ang reactance natin or impedance, or you can think of it as resistance, mababa. Okay, so kung mataas na mataas to, mababang mababa yung resistance natin, kumbaga, no? Na magiging wire na lang siya. Therefore, yung ating mga coupling capacitors are now considered to be short circuit. So itong pulang line na to, this represents the shorted out coupling capacitors. The next step is to draw the external resistances dito sa ating R sub E model. Unahin natin si R sub B. Si R sub B is placed in between the base and the ground. So this is your base. We can place here yung R sub B, and then this is the ground. This is R sub B equals 220 kilo ohms. Next, we have R sub E. R sub E is placed between the emitter and ground. This is the emitter. Lagay natin si R sub E, which is equal to 3.3 kilo ohms. And nandito yung isang terminal niya sa ground. Next, we have the collector terminal, which is directly connected to the ground. Therefore, we can place a ground here. So this is now the complete R sub E model for your common collector configuration. The input side for the R sub E model can be represented by a single resistance. Since ang ating input is being applied to the base, therefore, yung resistance natin doon or impedance can be represented using Z sub B. So this whole part can be represented by a single resistance, Z sub B. So this part is represented by this part. Next is we're going to apply an input voltage or an input signal. Ito yung AC, no, signal na gusto nating ipasok dun sa ating circuit, which is being applied to the input coupling capacitor connected to the base. Since we're applying an input voltage dito to your input side, magkakaroon tayo ngayon ng input current, which is I sub I. So let's write it down here. This is your I sub I. Of course, dito sa ating R sub E model, meron din tayong I sub I. So let's write it down, V sub I. If we're going to measure the impedance here, sa part na to, sa part ng base, this is your Z sub B. Ito yan. Okay? Ano kaya yung dumadaloy doon sa ating Z sub B na kuryente? Since connected din yung Z sub B sa base, ang dumadaloy na kuryente sa kanya is also I sub B. But what is the voltage across Z sub B? Z sub B, the voltage across Z sub B is also V sub I. Right? Next, babalik tayo dito sa ating R sub E model. So nag-apply tayo ng V sub I dito. Of course, ang voltahe mo dito is also V sub I. So between the base terminal and the ground, that's equal to V sub I. We have two equations for the input voltage V sub I. Unahin natin tong sum between the voltages, sum of the voltages rather, across beta RE and RE. What is the voltage across beta RE? It's I sub B times beta RE. What is the voltage across R sub E? That's equal to I sub E, which is yung AC, times R sub E. Alright, so let's write down the equation. Kasi kapag sinum up natin yung voltahe ng dalawang to, it will be equal to V sub I. We have V sub I equals voltage across beta RE, which is I sub B times beta RE, plus voltage across RE, which is equal to I sub E times R sub E. Alright. Punta naman tayo dito sa part ng Z sub B. We have V sub I, we have I sub B, and we have Z sub B. So napakadali lang ng kanyang equation. V sub I is equal to I times R. No? Ang resistance natin in this case is represented by Z sub B, or impedance at the base. This is equal to I sub B times Z sub B. We now have two equations for the input AC voltage. I-equate natin tong dalawang yan. Right? So, unahin muna natin to. Lagay natin sa left-hand side. We have I sub B times Z sub B is equal to, lalagay natin to sa right hand side, I sub B times beta RE plus IE times external resistance R sub E. Right. We can express I sub E in terms of I sub B para ma-cancel out natin yung I sub B na yon. We have I sub B times Z sub B is equal to I sub B beta R sub E plus, instead of using I sub E, ilalagay natin beta plus 1 times I sub B times R sub E. Therefore, we can cancel out yung mga IB na terms. Ang matitira na lang dito sa equation natin is Z sub B equals beta RE plus beta plus 1 RE. But since ang beta natin is in the range of hundreds, no? For example, 250. So 250 plus 1 is 251. Pero pwede natin i-approximate yung beta plus 1 na maging beta na lang. So let me just write it down here sa blank space na to, no? So we have Z sub B is equal to beta RE plus beta, instead of beta plus 1, actually approximately equal siya, no? Times R sub E. We can factor out beta, R sub E plus R sub E. So we have AC emitter resistance and the external resistor R sub E. So this is our equation to solve for Z sub B. Why is Z sub B important? Kasi Z sub B, kung mapapansin natin dito sa schematic or rather sa diagram na to, this is parallel with RB. Kapag pinarallel natin yung Z sub B and R sub B, makukuha natin yung input impedance Z sub I. Yan. So, ito yung ating Z sub I. So, that's why we should get the value of Z sub B. Let us now substitute the values of the resistances dito sa ating Z sub B equation in order for us to get its value. We have derived the Z sub B equation earlier. We have beta, so naka-factor out yung beta, no? AC emitter resistance plus the external resistance connected to the emitter terminal. I-substitute lang natin yung values. We have 12.62 ohms for R sub E na maliit, plus 3,300 ohms for R sub E, which is 3.3 kilo ohms. So, kinakailangan parehong naka-ohms yan or naka-kilo ohms bago natin sila i-add. Z sub B is equal to 331.26 kilo ohms. Now that we have solved for Z sub B, we can now solve for Z sub I or the input impedance. Babalik tayo dito sa diagram na to. Z sub B is parallel with R sub B. Yun ang ating Z sub I or the input impedance. Therefore, Z sub I is equal to 220K parallel with 331.26K, which is yung value ng ating Z sub B. Therefore, Z sub I is equal to 132.20 kilo ohms. As you noticed here, mataas yung ating input impedance for the common collector configuration. Next is we're going to derive a new equivalent circuit from the R sub E model. So meron tayong karagdagang equivalent circuit para sa common collector configuration. So these are the steps. Magsisimula tayo dito sa V sub I equation na ginagamit yung Z sub B. So we have V sub I, which is the input AC voltage. Ito yung ipinapasok nating signal sa input coupling capacitor. I sub B times Z sub B. First is, let us derive the equation for I sub B from this equation. So napakadali lang yan, no? We have I sub B is equal to V sub I over Z sub B. Alright. Now, write down the equation for I sub E, relating it to I sub B. We know that I sub E is equal to beta plus 1 times I sub B. Yung I sub B dito ngayon, ilalagay natin yung equation na to. We have I sub E is equal to beta plus 1 times, instead of I sub B, V sub I over Z sub B tayo ngayon. Alright. Next is, papalitan natin tong Z sub B equation, which is yung na-derive natin earlier. So we have I sub E is equal to beta plus 1 times V sub I divided by, di ba yung Z sub B equation natin, ganito yung itsura niya, beta times R sub E plus R sub E. Okay. But since beta plus 1 can be approximated as beta, magiging ganito yung ating equation. We have I sub E is approximately equal to beta V sub I over beta R sub E plus R sub E. Now we can cancel out beta in our equation. Therefore, I sub E is approximately equal to V sub I over R sub E plus R sub E. This will be our working equation para ma-derive natin yung panibagong circuit equivalent derived from the R sub E model of the common collector configuration. Now that we have derived the equation I sub E equals V sub I over R sub E plus R sub E, pwede na natin itong may translate into an equivalent circuit. Tignan natin yung equation. Yung R sub E plus R sub E, it implies na nakaseries yung dalawang resistor na yon. So, we can draw it in this manner. Nandito si R sub E, yung AC equivalent resistance, AC emitter resistance, no? And nandito yung ating R sub E na malaki. R sub E is equal to 1.26 kilo ohms and R sub E, yung external resistor, is equal to 3.3 kilo ohms. Kapag minultiply natin siya dun sa I sub E, it implies na yung I sub E ay dumadaan doon sa dalawang resistor na yon. Therefore, we can draw a current here na dumadaan sa R sub E tsaka sa R sub E. Alright? So this is your I sub E. Ibig sabihin din nito, yung V sub I, ina-apply natin sa pagitan ng terminals ng R sub E plus R sub E. Therefore, nandito yung ating input voltage na AC. So it's represented by the schematic symbol for an AC source. So this is your V sub I. This is the equivalent circuit of this equation. Alright? Next is, kukunin natin yung output impedance natin. To get the output impedance, we must zero out the signal source. So, paano natin i-zero out yung signal source na to? Di ba pag nag-zero out tayo ng mga voltage sources, nagko-connect tayo ng short circuit sa pagitan ng kanyang terminals. Alright? But again, as I've said before, hindi ito ginagawa sa real life. This is just used for computational purposes. Now, we will have an equivalent circuit na R sub E, and then this is your R sub E. Alright, so this is your output impedance Z sub O. Kasi meron pa tayong capacitor dito sa part na to, di ba? This one. This is R sub E, and meron tayong capacitor doon. Therefore, ang connection nila ngayon ay naka-parallel. Alright? So, in order for us to get Z out, we will get the parallel combination of R sub E and R sub E. So, ito yan. So, I already computed it. We have Z sub O, or the output impedance, is equal to 3.3 kilo ohms parallel with 1.26 kilo ohms. The output impedance is equal to 0.92 kilo ohms. So this is your output impedance. Lastly, we will solve for the voltage gain of the common collector configuration. Again, ito yung ating equivalent circuit, which is derived from the equation earlier. The next step here is to determine muna yung ating output voltage. No? Yung output voltage natin is taken from the R sub E resistor. Bakit? Dahil dito sa ating common collector configuration, ang output coupling capacitor ay nakakonect sa emitter. Alright, so huwag kayong malilito doon. No? Kapag common emitter, ang output coupling capacitor ay nasa collector. Kapag common collector, ang output coupling capacitor ay nasa emitter. And di ba under AC analysis or AC conditions, lahat ng capacitors are short circuit. So let's see, na-short out siya. Ang mamameasure natin dito is the output voltage, the output AC voltage, V sub O. Therefore, we have plus minus V sub O. That is the voltage across R sub E. Hindi ba't meron tayong voltage divider dito sa ating circuit or equivalent circuit, no? We have V sub I na hihiwalay or nahati sa pagitan ni R sub E and R sub E. We can write down the voltage divider equation with this one. We have V sub I, or the total voltage, divided by the total resistance, which is equal to R sub E plus R sub E, equals the voltage at a certain point divided by the resistance at that certain point. Ang concern natin is C output voltage. So ilalagay natin dito V sub O divided by yung resistance niya ay R sub E. Alright. Ang concern natin dito is yung voltage gain. The voltage gain is equal to the output voltage divided by the input voltage. So dito pa lang makukuha na natin yung ratio between the output voltage and the input voltage. So let me just write down the equation for the voltage gain on this side. We have output voltage divided by the input voltage. So i-rearrange lang natin tong equation na to. We have R sub E, which is the external resistor connected to the emitter, divided by AC emitter resistance plus R sub E. So this is the working equation for the voltage gain of the common collector configuration. We can now substitute the values of R sub E and R sub E, no, the AC emitter resistance and the external resistor R sub E. Solving for the voltage gain of the common collector circuit or configuration, we have the voltage gain is equal to 0.996. So this is 0.996, which is still approximately equal to 1. That's why the voltage gain of the common collector configuration is approximately equal to 1. Anong ibig sabihin nun? Ibig sabihin nun, approximately kung anong ipinasok natin sa input coupling capacitor natin, more likely, yun din ang lalabas sa ating output coupling capacitor. But again, as I've said, anong silbi nun? Bakit ginagamit pa natin yung common collector configuration? Kung ano pala ipinasok, yun din yung lalabas. Again, the purpose of the common collector configuration or the common collector circuit is to be or to act as an impedance matching circuit or impedance matching device. So let me just recap on that para mas maintindihan natin. For example, meron tayong isang amplifier circuit, no? Let's say common emitter or common base. Let's represent that as a block na lang para mas madali. Meron tayong input signal here. Let's say a small AC signal. Anong expected output natin? Siyempre, yung output niya is amplified. No, the output voltage is being amplified. For example, kung common emitter siya, ganito yung more likely magiging itsura ng kanyang output. Out of phase by 180 degrees and then amplified yung kanyang values. Alright? So let's say this is a common emitter, for example. Common emitter circuit. Whether it is fixed bias, emitter stabilized, so on and so forth. What if we connected a small load, a small value ng load dito sa ating output? Let's say, yan. So maliit lang, let's say 8 ohms. No? Sa practical applications, yung mga ganyang kaliliit na load, nakikita natin sa mga audio systems. No? Halimbawa, yung load na yan ay isang speaker. So meron tayo, for example, 4 ohms, 8 ohms, 16 ohms na speaker, which is mababa. Parang wire na lang. So, ang nangyari is, almost na short out yung ating signal. Instead na ganito yung magiging signal natin, since mababa yung ating load, ay baka maging ganito na lang. So, maliit na lang. So, almost flat na. No, nagzi-zero out. Almost nagzi-zero yung ating signal. So, mababang-mababa na lang. This is called loading effect. Yung loading effect, ito yung pagbaba ng voltahe dahil mababa yung ating load. Ngayon, para magkaroon tayo ng match, kasi this is a high impedance source and low impedance load. Para hindi mag-zero out or bumaba yung ating output signal or output voltage, maglalagay tayo ng circuit sa pagitan nila to match the impedance. Okay? At yun ang role ng common collector circuit, which is an impedance matching circuit. So maglalagay tayo dito ngayon. Let me just draw the block of the common collector, no, para mas simple yung ating analysis. And then, this is your load na mababa. Let's say 8 ohms. So, it represents a speaker. So, kung ano yung pumasok dito sa common collector, yun din yung lalabas more likely dito, which we have proven kanina dun sa ating derivation for the voltage gain. So, yun ang role ng common collector. It's used as an impedance matching circuit para maiwasan ang loading effect. That would be all for now. Have a nice day.